Hello, Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Muhammad Farith bin Halim, and today I am going to present my UGP title, which is FE Analysis of Disc Brake Squirrel with the Inclusion of Temperature Effect. My supervisor is Dr. Abdul Rahim bin Abu Bakar. Okay, this is for the introduction. The disc brake system usually consists of disc brake, pad, friction mat, backplate, caliper, carrier, piston, bolt, and guide pin. The disc brake operates such that the pad is forced against both sides of the disc, causing it to slow down. Better stopping performance than the drum brake. That is said by Sarkar, Praveen, and Modi in 2014. So this is the picture of the disc brake. The brake pad, set of brake pad, disc, carrier and caliper, brakes, caliper cylinder, and also the other component. For the background study, brake squirrel generation leads to increase in cost warranty claims for manufacturer. And brake squirrels always occur at a frequency above 1 kHz and is described as sound pressure level above 70 decibels. And disc brake and pads are subjected to high thermal stress due to high amount of energy converted from mechanical to thermal. This is the example of figure where the disc brake, how the heat is dissipated from the disc brake. As you can see, heat is generated from the disc rotor and heat is, as you can see, heat is generated from the pad to the disc rotor and dissipated through the lining of the disc rotor. Convection and radiation happen on the surface of the disc rotor. Okay, so the problem statement is brake noise can be a little annoying, especially to the driver during the braking. So the study of brake squirrel has been studied for generation, and approach for thermal has always been excluded. Why is that? This is due to complex phenomenon of heat transfer and numerical computation of temperature field for disc brake. This is said by Dr. Abu Bakar in 2019. So my objective of this project is to predict and compare disc brake noise squirrel with and without the temperature effect. And the scopes of the project are this. The first one is to predict the brake noise generation by using complex agent value analysis. Second one is to consider the brake noise frequency of interest from 1000 Hz up to 15,000 Hz. The third one is to consider maximum temperature up to 250 degree. The fourth one is to conduct brake tests to determine the temperature for each components in the brake assembly. The fifth one is to conduct simulation based on parameter of vehicle speed of 3 and 10 km per hour and pressure up to 1.5 megapascal. Sorry about that. Okay. Let's go to the methodology. The methodology is divided into two parts, which is for FYP1 and FYP2. During the FYP1, I completed the CAD model of brake assembly by using the SolidWorks. Next is finite element method in the Abacus software, and the complex agent value analysis is done without the temperature input. And these are the parameters that I use to simulate the finite element model. There are pressure, friction, and also sliding speed. So the analysis that I want to find out is the unstable frequency exerted from the brake assembly, the unstable modes related to the unstable frequency, and also the contact analysis of the brake pad and also brake disc. Following that, during FYP2, I do an experimental work to know the temperature distribution, to know the temperature distribution for all the components. The data for the temperature will be used for the finite element analysis to conduct a complex agent value analysis. where this cycle is returned back, I want to study the unstable frequency, unstable modes, and also contact analysis with the inclusion of the temperatures. And the final results will be discussed. Okay. So this is the CAD model and FE development. Okay, these are the brake assembly at the auto lab, and these are the CAD SolidWorks and also the finite element model, Abacus version 6.4. Okay, for the finite element models, I divided the finite element model into 3 types of model. The first models are the temperature included in all of the components. The second model is the temperature included for disc and brake pad, and also the third model is for the non-temperature model. So, for the experimental setup, these are the table that I use to gather the data. As you can see, the temperature of all the components is measured based on the temperature of this. So, when the disc is 50 degrees, I measured the data from the thermocouple display for the caliper, pad friction mat, pad backplate, and also carrier. This is done for the pressure of 0.5 until 1.5 megapascal, and also speed from 40 rpm until 130 rpm. Okay. So this is for the results and discussion. I've divided the result and discussion into 3 parts, which is the CEA results, contact analysis, and also the comparison CEA and test. The comparison of CEA and test are done to validate the finite element model. Okay. So, the complex agent value analysis. The 3 FE models has been undergo the complex agent value analysis, and from the result of the simulation, the graph is tabulated based on the existing real part. From this graph, we can say that the FE model 2 has the highest total real part, followed by FE model 1, and lastly is FE model 3. This is the raw data of the total number of real part. You can see that the total number of real part for this and pad only, which is FE model 2, is 89. All component is 63, and also the non-temperature is 18. Following that, the unstable modes at square frequency. For FE model 1, the unstable mode is based on the highest real part value. So, this is the results of the simulation at the operating temperature of 50 degrees Celsius, pressure of 1.0 megapascal, and also a speed of 3 km per hour. From this figure, we can say that the shape of the component has been distorted severely. The disc seems to be in a bending mode, and also the pad friction material of the brake pad has a spiky feature, and all the component seems to be deformed severely. Next is the FE model 2. From this, we can see that the disc experience the most displacement at here, and also the pad seems to bend outward from its original shape. Continuing that, for FE model 3, which is for the non-temperature, the pressure is 0.5 megapascal, and also the speed is 10 km per hour. From this, we can say that all the components experience bending mode, and the most displacement occur at the caliper, the inside body of the caliper. In addition, the brake pad also undergo bending mode severely, and the shape has been distorted. Next is contact analysis for all for two FE model, which is FE model 1 and FE model 2. So this is for the FE model 1. The pressure applied is 0.5 megapascal and also the velocity is 3 km per hour. From this we can see that the pressure exerted on the surface of the brake pad is 0.6 megapascal for FE model 2, while 0.45 for FE model 1. Also, the pressure exerted on the disc for FE model 2 is 1.1 megapascal and 0.6 megapascal for FE model 2. The area of distribution for the pressure is also bigger at FE model 2 compared to FE model 1. Next is for the pressure of 1.0 megapascal and also velocity of 3 km per hour. The pressure exerted on the surface of the brake pad is 1.09 megapascal for FE model 2 and 0.955 for FE model 1. For the disc, the pressure exerted is 0.64 megapascal for FE model 2 and 0.51 megapascal for FE model 1. The last one is for pressure 1.5 megapascal and velocity of 3 km per hour. The pressure exerted for FE model 2 is 2.3 megapascal, but for FE model 1 is only 1.7 megapascal. For the pressure on the disc, on the surface of the disc, the pressure exerted is 3.73 megapascal and for FE model 2 and 1.33 megapascal for FE model 1. We can say that the FE model 2 possess a stronger pressure exerted on both disc and brake pad compared to the FE model 1. Also, the pressure exerted on the brake pad is much smaller than the pressure exerted on the disc. So, the results of the FE models will be compared with the test data from Satya 2020. This comparison is done to validate the FE model so that we can know the model, whether the model is accurate or not with the brake model. So from this graph we can say that there is a chance of similarity between these two trend graphs. From that graph, the percentage of average error has been analyzed, and these are the results. For school experiment results, there are 4 school experiment results that are similar to all the 3 FE models, which are 4511, 4521, 8652, and also 9063. So for FE model number 1, the average error is 0.25%. FE model 2 is 0.31%, and also FE model 3 is 11.27%. So from this analysis, the average error for FE model 1 is the least compared to the FE model 2 and also FE model 3. It can be said that the most similar representation of the FE model is FE model number 1, followed by FE model number 2, and lastly is FE model number 3. So in conclusion, the objective to predict and compare the brake noise coil with and without the temperature effect has been achieved, and it is found out that the FE model that generates unstable frequencies is higher when temperature is included. Also, 3 FE models have been simulated, and it is shown that FE model 1, which is the model that included all the temperature of the component, possesses a closer model to the real brake disc. So for the future work, maybe consider to use thermal imaging cameras so that the temperature measure is more detailed, and also to consider knuckle and wheel hub in the FEA of the component. The prediction of the scroll frequency might be different. That's all from me. Thank you for listening. Thank you.